So I want to talk about three things. One is the temperature and behavior of lava. This is actually what I study. So as Dee mentioned, originally I used to study magma, which many of you will know as molten rock underground. And I used to study that because I was interested in how the large blobs of granite in the Himalaya formed, for example. I've always liked mountains. Yeah, so I started studying the rheology, how magma flows and moves, right? And so then I found that it was indeed actually a lot easier to get funding to study lava because people care more about that for obvious reasons. And so I kind of transitioned from magma underground to magma out of the ground. It's all closely related, similar experiments. Then I'll talk about kind of different kinds of volcanoes. Now, there are many, but there are really two really important kinds that we need to distinguish. Most easily referred to as the red and the gray. So the red volcanoes are things like at Hawaii, where you have rivers of fire. You can describe them as poetically as you want. And they're usually, not always, but usually actually relatively safe in that you can see it coming and you can get out of the way. The gray volcanoes, the big ash explosions, are more dangerous, often less predictable, and can have more far-reaching consequences. So I want to talk about them, show you some video and some examples. And then finally, I want to talk about how often volcanoes erupt. We'll talk about something called recurrence interval, which is something that is something we think about with regard to many kinds of geological hazards, right? So hurricanes, volcanoes, earthquakes, asteroid impacts. These are all things where we can look statistically over time and say how frequently a disaster of a particular magnitude is likely to happen. And sometimes we need to recalibrate. You may notice that we've had a lot of 100-year floods recently that should really only happen every 100 years, and that's because we need to adjust our idea of just how bad a 100-year flood really is. Anyway, so I'll start just by talking a bit about what is lava, and I will share some with you. So lava is molten rock, and rock is made of silicate for the most part. So sand, most sand grains are actually grains of quartz, which is silicon dioxide. Silicon dioxide is the most important chemical component in lava and magma and most rocks. When it's molten, it's kind of moving around. It's actually quite well bonded together, which makes it quite sticky, but it can flow. As it cools down, it becomes stickier and stickier. If you cool it quickly, it will quench and form glass. So I have two pieces of glass here that I'm going to pass around. One is pretty much transparent. This is man-made glass. And it was discarded as a failure because it has a few crystals in it. This is a natural obsidian glass from California, erupted about 800 years ago. And this is from a lava flow. You can see this also has crystals in it, kind of whitish gray spots. It also has really nice swirly flow bands. It looks like kind of stirring a really thick custard or gravy, which is pretty much what this was like when it came out, only much hotter. So if you cool it slowly, it will crystallize. If you cool it quickly, you can quench it to glass. Anyway, I like those two as a pair together because you can actually see the three-dimensional shape of the crystals in the man-made glass. So that's the top left and top middle samples. I've got a couple more that I'm going to pass around. Now I'll pass around the granite. This is what I always used to study. This particular granite is in fact from southeast Missouri, from just outside Elephant Rock State Park, because it would be naughty to take it from the park. This is the Graniteville granite, about 1.4 billion years old. So it's pink because it has a lot of feldspar in it. Feldspar, again, is mostly made of silica. And this is fully crystalline. That's what happens when magma cools slowly underground. So these, the granite and the obsidian, and we'll get to see it later, the pumice as well, these all have the same composition, but they look different. They have different properties because of how they formed, right? So the granite cooled slowly underground and crystallized. The obsidian cooled more rapidly above ground as a lava flow and quenched mostly to glass. The pumice we'll talk about a bit later on. Another common question is, how hot is lava, right? We know you should not touch lava, but how hot is it? So for this, we need to, first of all, decide what temperature scale we're going to use. This is one of my favorite ways to choose which temperature scale to use. So we've got Fahrenheit, Celsius, and Kelvin are the three that you'll most commonly find. Yeah, so actually in science, we normally use Kelvin. Of course, we're up right now in this room. It's around 300 Kelvin, so we're not dead, so that's good. But it's really important to think about temperature scales. I remember a few years ago, Monday Night Football, John Madden, they were in Arizona, and the week before they'd been in Green Bay. And John Madden said it was literally 3 times as hot in Arizona as it had been in Green Bay the previous week. Because, I don't know, the temperature was like 80 versus 27 or something. Like, no, it's not. So I put together the different scales right here, just to show you how the numbers stack up, right? So Celsius and Kelvin, of course, have the same spacing. They're just offset by 273.15. And then Fahrenheit is a different spacing, right? So a degree Fahrenheit is only just over half a degree C in terms of an incremental change. So it helps to be fluent in many different kinds of units, and actually geologists have an odd mixture of units that we use, partly because although we really are a science, we also do interface quite a lot with engineering, and there's obviously been a lot of geology developed both in Europe and in the US, so we have a rather odd mixture of units. We're usually more bilingual about these things than some other disciplines. Anyway. So at this left end, this is kind of space, right? So that's obviously very, very cold. This is the range of outside temperatures in Missouri in a typical year, from one of the coldest days around 0 Fahrenheit or just below, to a hot day would be a little bit above 100 Fahrenheit. The oven that I'll cook my kids' pizza in later is going to be at around 400 Fahrenheit, something like that, maybe 425 if they want it crispier. And so you can see that the spacing between outer space, outside in Missouri, and inside the pizza oven, it's kind of a similar spacing. You have to go several more over here before you get to the cool end of lava. So rhyolite is kind of the lower temperature end of lava, and that obsidian is actually, the composition is rhyolite. So that would have erupted at around 800 Celsius, around 1500 Fahrenheit. Something like that, about 1050 Kelvin. And then as we go up to the hot end, like Hawaii, for example, a very hot, glowing fluid lava we see there, that erupts close to 1300 C or 1550 Kelvin, or approaching 2400 degrees Fahrenheit. So it's really very hot. There is a lot of heat energy stored in lava. And of course, actually, volcanic eruptions is one way that the Earth cools down. So a lot of what happens in Earth's interior is all about trying to lose the heat from the inside, get it to the outside. Okay, I've got a lot of YouTube videos. I don't know how well these are going to work, so fingers crossed. But what I study is how lava behaves in terms of its rheology. So that really means how it flows. So does it behave like a solid or a liquid? So we know at room temperature, rocks are pretty hard things, right? And if you hit them hard enough, they will crack. So that's called brittle behavior. Rocks, when they get very hot, even crystalline rocks like that granite, when they get very hot, they can actually flow very slowly over geological timescales. Lava, of course, being molten, can flow much more quickly, again, over a timescale that we can appreciate. But there are some interesting transitions between fluid and so this is a video that we shot at Kaya in Guatemala. Oh no, I can see it, but you can't. maybe some. It takes my laptop about 10 seconds. We'll get that. So I'm going to show you some videos from Kilauea in Hawaii and from Pacaya in Guatemala. I'm just going to do them all at once, I think, so I have to keep jumping back.
How do we change an unjust system? A criminal justice system.
Okay, so we're looking down on this lava flow. The black dot you can see, or several of them, these are boulders of lava. Right, so remember, lava is really dense. If you fall onto a lava flow, you are not going to sink into it. You are just going to cook on the surface. Anyway, we can use these boulders and knowing the width of the channel to determine the speed at which the lava was flowing. And we can use some simple physical equations to get the speed of flow. This is sampling lava on Hawaii. This is my PhD students wielding the hammer right there.
We are the solution.
And
we can vote
pouring water on it to cool it down. That's actually all our drinking water for the day.
We can do
yeah, Alex looks really pleased there. He was less pleased an hour later when we were really thirsty. Anyway, this is back to the lava flow in Pacaya. This is the other end of that lava flow. So we saw it was flowing really fast like a river. This is the front of that lava flow. And here by now it's cooled down. It's still glowing, it's incandescent, which means it's at least 900 degrees, but it's not really going anywhere. This is me I've just grabbed a piece off the edge of the lava flow. You can see it's really hard. Right, I'm smacking it pretty hard with my geology hammer, not putting my foot on it, because that would be, it would make it easier to break, but my foot would catch fire. So you crack it open, and you can see it's still incandescent, red hot on the inside. But it is that hard at that point. You know, even though it's still 900 degrees, it needs to be hit really hard with a hammer. This is there we go. We don't need to use that one right there. All right, so that one. I always like it.
Whoa.
Gives you an idea of like how loopy lava is. You can still see it like in the background. You can still see it oozing. Right? So it's moving, but it really requires a hammer. And the main thing we forget is that this lava is nearly 3 times as dense as water. So although it's kind of sticky like syrup, it's a lot heavier than syrup. Well, I might as well show you this one now. I was going to save it for a bit later, but this shows you the advance of a lava flow. This is from the summer. That's a Mustang. Not that it really matters. But, that's R2-D2. I'm not sure what he's doing there, but
I know it's going to pop. That's why I came to this next pole.
Still red.
Anyway, so this gives you an idea. This is obviously time-lapsed, so it took maybe 20 minutes. Elsewhere, you can find the whole unedited thing. And this lava is moving pretty slowly, but clearly not much is going to stop it and get in its way. So that's the flow front. Now, further back behind that, we had lava that was really. This is the most amazing lava flow I've ever seen.
Really big plane from Fuego.
It's funded by an individual attorney and creates a research institute that only he...
Take a look at this
All right,
incredible
so,
video from the Big Island.
Yeah,
of
so this
Hawaii.
was the famous Fissure 8, and this is the fastest lava flow that. Yeah, that's real time. That's not speeded up. You can see the people walking. It's going. I believe it was around 25 meters per second, which I should have converted that to miles per hour. Anyway, it's really fast. That's Hawaii this summer.
Now, when you have a second, take a look to your right.
Yeah, so, and the difference you see there is not that it's different material, it's that it's, one is lava that's just come out of the vent and is flowing in a channel. The channel insulates it because it's surrounded by more lava that had already come out. And it stays very hot, and it can move very, very fast. And then, go back to this. The flow front, where it's advancing, where it consumed the car, that front has cooled down a lot. So the lava is much, much more viscous, moves much more slowly. But again, it's pretty much unstoppable. But the key thing there is you can get out of the way. I mean, you won't save your house. I mean, you would think you could save your car, but anyway, but it's not really a hazard to life and limb, except for people going and looking too close. Here's another example of, and this won't necessarily look like a lava flow initially. Let me just explain where we are. This is Santiaguito in Guatemala. This is a lava flow right here. It's not really moving very much at all. It moves a few meters a day at most. It's incredibly viscous. It's quite cold. It's still just liquid, and it's just able to flow because it's on quite a steep slope. It moves very slowly. And at the surface, all you see is rocks falling down. The inside, though, is still, if we could see it, it would be incandescent. It would be very, very hot. And it would be just viscous enough to actually be flowing. But the outer part of the flow is cold and now brittle and breaks into blocks that fall down. But I want you to watch this block. This is also one of the coolest bits of video I've ever seen. I was here when it was recorded, and I'm really gutted that I didn't actually manage to record this particular thing, but my friend Julio did, luckily. So, a piece of rock falls down. Watch this big boulder as it gets to the bottom. You can see it's actually still hot. And it's like a watermelon. It just goes sploosh. That is just... and here's another interesting thing, which is the way that things deform depends on the strain rate. So here, there was quite a high strain rate applied as it hit another rock, and then suddenly it behaves a lot more like a liquid than a solid. Before that, it was just bouncing down, and Anyway, so oh yeah, I was going to pass around a piece of basalt lava flow. So this is what a piece of lava looks like. The flat face is where I sawed it. We have diamond-coated saws in the geology building that we can use to slice rocks open. And the main thing I want you to see is that there's bubbles and there's crystals, and then there's a lot of just dark, fairly glassy stuff. This is, and feel the density as well. This is how heavy lava is. Okay, so we've established that lava is very hot, but all we've really looked at so far is lava flows. I have a few more videos of lava flows for you, but we need to recognize that some volcanoes tend to erupt in a rather different way. So if you remember Mount St. Helens, for example, or in 1980, Pinatubo in 1991, or some of the more recent ones, especially in South America, usually what we see on the news is actually clouds of ash. In Hawaii, we saw lava flows, and there's a few other volcanoes around the world where we see lava flows. But I think eruptions that produce ash are actually more common. So we've actually got 3 different types shown here, but cinder cones, these are very small. Right? So these might be 1,000 feet high and a couple of miles across. If you're ever on I-25 in northern New Mexico, take the short detour to go visit Capulin Volcano National Monument. Just on the east side, it's close to the Oklahoma border. It's got a little spiral road you can drive around up to the top, and you get a wonderful view of lots of other cinder cones. These are very young. It's an area where, probably the closest area to us where there's likely to be more volcanoes in the future, and there'll probably be more volcanoes that are about this size. So Capulin itself is one of the youngest in the field. It's about 50,000 years old, plus or minus. But the field's been active for 2 million years, so the chances are that another volcano will grow there. Anyway, so cinder cones are nice, but they're not tremendously hazardous. The two main kinds I want to distinguish are shield volcanoes, and that's a cross-section of Mauna Loa, which forms most of the big island of Hawaii up on top. It's called a shield volcano because apparently it looks like a Roman shield laid down. It's got very gentle slopes because it's built of very fluid lava flows that can spread out very thin and flow long distances, and it's huge. From the base of the seafloor to the summit of Mauna Loa, which is, with a volcano, you can measure its height quite easily. You take whatever the land surface was before the volcano formed, and then the summit of the volcano, that's its height. It's 9 kilometers. It's actually slightly higher than Mount Everest is above sea level. The thing about Mount Everest is, what do you use as a reference point for the height of Mount Everest? We use sea level, but that's not a very good thing to use because sea level's changing all the time. Right now it's rising, so actually Mount Everest will gradually get lower and lower above sea level. But anyway, the point is Mauna Loa is enormous, right? And it's 100 miles across, and it's about 6 miles high, rising from the seafloor. A huge volume of magma. Compare that with Mount Rainier, which is kind of traced inside Mauna Loa there. Mount Rainier is a big volcano. If you've ever been to Seattle, you will have seen it. Mount Hood over Portland, Mount Fuji in Japan, all these classic pointy volcanoes are what we call stratovolcanoes, which are layered. And they do produce lava flows, but they also produce lots and lots of ash. And they tend to be more viscous, so the lava is stickier, it doesn't flow as far, and we get a narrower and steeper volcano. And so those are the volcanoes that typically produce ash and big explosions. Let's talk about shield volcanoes first, since we're already looking at video of Hawaiian lava flows. So this is Mauna Loa, taken from Mauna Kea. These are actually some little cinder cones around the base of Mauna Kea. Again, you can see it's got a pretty gentle slope, even though it's really high, right? The summit of that is about 14,000 feet above sea level. Deceptive. Here's an eruption on Mauna Loa in 1975. So when magma reaches the surface and becomes lava, it can get to the surface either in a crack or a pipe. If it gets to the surface in a crack, we call that a fissure eruption. And we get something like this. This one was about a mile long. And then usually they rapidly neck down to kind of 6 or to a few discrete points rather than having a whole solid curtain of lava. If they come out in a more of a pipe, this is Pu'u'o'o, which is actually one of the vents of Kilauea volcano on Hawaii. It's from 1983. And then you get like basically a hose pipe of lava coming out of the ground, and it looks lovely. And then, off the lava flows. It very quickly organizes itself into channels, and we can get very fluid-looking lava like this. Again, this is usually up closer to the vent where it's very hot and fluid. As we get closer to the toe where it's cooled down, we get a different kind. So we use 2 Hawaiian words to describe these textures. This one is called pahoihoi, and this is called a'a, which is also the noise you make if you trip over when walking on it, because it's extremely pointy, all these jaggedy blocks. This is 2 USGS, US Geological Survey scientists. You can tell that although they're not going to hang around there because it's probably very hot, they're not in imminent danger of being caught up by that lava flow. As we saw with the car and crossing the road and everything, lava does not obey road signs. It will just keep coming. It doesn't care what's in the way. So let's just look at these different textures of lava as they form. So this is pahoihoi as it's starting to cool and slow down. But you can see it's got this ropey texture to it. On the other hand, is kind of is colder. It can't flow coherently. It has to break. And so we get these blocks. We usually think about lava flowing on the surface, but when you get somewhere like Hawaii, lava flows not only over the existing lava, but also underneath the existing lava in lava tubes. And these can form, actually, if you have an open channel and lava starts to cool on the side of the channel, and you get kind of a cool shell that gradually builds out and completely covers the channel. And sometimes the roof of the channel will collapse, and you'll get what we call a skylight, and you can look in. And usually the lava that is in these is very well insulated, so it's still very hot and fluid and can flow very fast. Then afterwards, the lava just drains out, and you're left with a tube. So this is a lava tube actually near Mount St. Helens in Washington State. One interesting thing here, you can see lava sickles on the roof, just like icicles, but they're actually frozen drips of lava. And on the floor, you can see that it's kind of got a keyhole shape. And so initially it was a tube, but you get thermal erosion. The lava actually remelts what it's flowing over and wears its way down. It's a combination of thermal and mechanical erosion, but you get this, this kind of keyhole shape. There's a lot of interest in lava tubes. The reason that NASA funds some of my work, for example, is there's a lot of interest in lava tubes on the moon. If we set up a lunar base, the most likely place that we'll choose to begin with is actually a lava tube, because then you have a roof that protects you from cosmic rays. This is the eruption from this summer, just various images showing, you know, it's really quite spectacular. You know, very, very difficult for the people that live there, of course. A great opportunity for scientists to study lava flows, and just quite a spectacular thing to look at as well. So this is a map showing the extent of the lavas from this summer. So the pink area is the flows from this summer. The purpley lilac stuff is older flows with various dates on there, but 2014, 1840, 1960, 1955, all this is the East Rift Zone of Kilauea. So this is basically a long fissure. The summit of the volcano is over here, but lava travels along this crack and can pop out at any time. But since the entire island is built of lava, I mean, there's really no secret on Hawaii that you're living on a volcano. The island wouldn't be there if it weren't for the volcanoes. But there's always a question of where can you live that is safe? And the East Rift Zone is not one of those places. All right, so we already saw the Mustang and the fast flows at Fissure 8. So now I want to talk about gas bubbles. So in lava, we've got molten rock, and we have solid crystals, but we also often have gas bubbles. Sometimes you'll just have a few, and these are gas bubbles bursting at Hawaii, and they look absolutely fantastic, make for great pictures, not really threatening anybody. The drips that get thrown off form these things called Pele's hair and Pele's tears. So basically, these are drops of lava that have these long, thin tails. Usually the tails break off, and they form Pele's hair, which you can just find it blows around. And if you look under rocks or along a curb on a road, for example, you'll find mats of Pele's hair. And then Pele's tears are kind of the teardrop-shaped heads of these droplets. So, that's very nice. But sometimes we have magma that has a lot of gas in it. And we have enough that we have an explosive eruption. So what you need to know here is that you can dissolve more water in magma at high pressure than you can at low pressure. So since magmas form at high pressure, they can often have quite a lot of water dissolved in them. As they ascend towards the surface and the pressure decreases, they can no longer keep all that water dissolved, and we start to get bubbles of water forming. Now, I say bubbles of water. Obviously, this is in magma at very high temperatures, so this is really steam, but it's very dense steam. And depending on the conditions, it may be a supercritical fluid. But anyway, it's basically water vapor. The bubbles, when they first form, let's say at B, this is the level at which we can no longer keep everything dissolved. As the magma rises, those bubbles are going to expand. Many of you will know the ideal gas law, PV equals nRT. So if we're keeping the temperature the same, but we're decreasing the pressure, the volume of the bubble is going to increase as it rises up the conduit towards the surface. Also, the shallower we get, the less water we can dissolve in the magma, and even more water is going to form new bubbles. So we have bubbles growing and bubbles expanding, and this continues and continues until we get something that is really now a foam. So this is a piece of pumice, and this is a piece of foamy magma, which is mostly air bubbles. And because those bubbles, for the most part, are isolated, they don't interconnect, that's why you can throw pumice into the sea or a bath or something, and it will float. So I've collected pumice from Krakatoa. It's just floating there in the sea. Like Atitlan in Guatemala, it's like 86,000 years old eruption. The pumice that's in the lake there isn't still in the lake from that eruption, but it's pumice that gets washed in there from the surrounding deposits every year, and it's because they have flash floods, and it just floats around in the lake. You can just go around in a boat, pick it up. Same thing with that. At some point, you get so many bubbles that you can no longer have a stable foam, and it will fragment. And we go from foam to gas with little bits of melt in between. Those bits of melt are going to quench very quickly. Right? When that happens, they'll cool down because they will also accelerate out of the vent very quickly at that point, be thrown out into the atmosphere. They'll cool down, and they will quench to glass. So yeah, just to remind you, here's our pumice, which has a lot of bubbles but is not yet actually fragmented. If it does fragment, we get particles that look like this. On the top, you can see these little three-pointed things. Remember what the shape of the gap between the bubbles was, right? If you're a piece of magma trapped between 3 or 4 bubbles, you're going to have kind of a 4-pointed star shape. How many of you watch ninja movies? You know what caltrops are? Little things that ninjas carry around, little 4-pointed stars, right? You just scatter them on the ground. They always have a point sticking up. So if you want to catch other ninjas, you just scatter these on the ground. And anyway, watch more ninja movies. All right. So this is the shape of volcanic ash particles, right? Because volcanic ash is actually volcanic glass, and it has these little pointy shapes. That's why it's so very, very bad to breathe it in. These are particles from Vesuvius, right, looked at in a scanning electron microscope. Actually, most of these are crystals, and they're not the really pointy shape. They're still really bad for you, and a lot of these are small enough to inhale. So if they're smaller than about 4 microns, you can inhale them. So when you get these little pointy things, and they're small, they'll go right down into your lungs. They will cut you, and then they will form concrete in your lungs as well. So really bad news. That's why the gray volcanoes are more dangerous. So I've got a few pictures of erupting explosive eruptions. That's a small one in Santiaguito. Again, the lava flow we looked at before with the rock that behaved like a watermelon, that was just down here on this lava flow. So Santiaguito produces lava flows, and it erupts explosively several times a day. So it's very close to Quetzaltenango. So the second city of Guatemala is actually just behind us in this field of view. So we're looking out towards the Pacific Ocean. But yeah, you can see the Mexican border from on top. Yeah. So yeah, that's Santiaguito. So this big crater, by the way, formed in 1902. The biggest explosion of the 20th century of any kind happened when the volcano we're standing on, Santa Maria, half of it blew away, but it left the old summit behind, which is what we're stood on. In the crater that was left behind, these lava domes started to form in 1922, and they've been growing ever since. It's rather similar to Mount St. Helens, except Mount St. Helens blew its top off, this blew its side off instead. Vesuvius, I love old pictures of erupting volcanoes, lithographs and stuff. This is a more recent picture of Vesuvius erupting. This is 1944, and those are US Air Force planes flying past it. And that's Mount St. Helens in 1980. So what's inside? These are your classic pointy volcanoes, look a bit more like Mount Doom. In fact, if you do want to go on a geological critique of Lord of the Rings, Mount Doom is very pointy, yet produces lots of lava flows. It should be a shield volcano like Mauna Loa, not a pointy volcano. But anyway, that's all right. So stratovolcano, again, the name strato means layered, just like geological strata. And we have alternating layers of usually quite thick lava flows, and then lots of ash. And the lava flows manage to keep the ash together and allow a big volcano to build up, but they are often actually quite unstable, and they can explode or collapse. This happens quite frequently. Until they do, though, they look, some of them are just amazingly symmetrical. This is Agua in Guatemala. Next to it, this is actually taken from Fuego, which means fire, which is the one that erupted also this summer and killed quite a few people. Agua means water, of course. It's one of the more symmetrical stratovolcanoes in the world. Other famous ones include Etna in Sicily. This is a photo taken from the International Space Station. And then Santiaguito again. This is taken from the lava flow looking up towards the summit of Santiaguito. And we have three things happening in this photo, and one of these we're going to devote a bit the next few minutes to talking about. Down this side, we have rockfall. Okay, that happens. Volcanoes are very unstable masses of rock, and things fall off quite frequently. We also have an eruption column going upwards. Okay, that's fairly normal. We saw one of them before. But we also have this cloud coming down the side, and it's coming down pretty fast, and it's starting to grow and actually producing a whole nother cloud over here. This is what's called a pyroclastic flow. The old word is a nuée ardente, which is a glowing cloud in French. So, thank you. So these pyroclastic density currents, this is what happens. They can form in a couple of different ways, but most commonly, you get an eruption column of hot gas and ash that, if it's got a lot of ash in it, it's actually pretty dense, right? Remember that the ash particles are 3 times as dense as water. So you don't need a whole lot of ash in that mixture to make that cloud dense, and it can fall down the side of the volcano. And that's usually what happens. Volcanoes are often very steep-sided. It will roll down very fast. They've been observed going more than 200 kilometers per hour. We know that they can travel more than 100 kilometers over the right terrain. We've not witnessed one that's gone that far in recorded history, but we've got plenty of evidence in the geologic record. And we infer speeds of, in some cases, over 200 meters per second, or 700 kilometers per hour. A famous example, also 1902, was a bad year for volcano disasters. Mount Pele in Martinique destroyed the town of Saint-Pierre, which was apparently known as the Paris of the Caribbean. Reading about it. 28,000 people, and only 2 survived. That's what's left of the town, and that's the cloud coming down the side of the mountain and going into the Caribbean. And one of the 2 survivors was the guy who was in the town jail, so he was insulated from the heat, but he went mad. He thought that he was literally in hell because it was completely dark. He was slowly being cooked. It smelled of sulfur. He was pretty badly burned and completely traumatized. And then I think he went around with, I think it was Barnum and Bailey's or Ripley's Believe It or Not or something. Anyway, I've got a couple of videos of pyroclastic flows. So let's hop out of PowerPoint again, because they're really impressive things. How many of you have seen Dante's Peak? Pierce Brosnan? Only a few of you willing to admit it. All right. So at the beginning of Dante's Peak, when he's driving the Jeep trying to outrun the volcano, it's a pyroclastic flow that he's trying to outrun and or outdrive. And in general, the pyroclastic flow is usually going to win.
I'm no computer here, and this is how you circuit bend a Bible. Right, let's get it open. So this is the Wonder Bible. It's rather wondrous, and it's got a lot of packaging. It's rather packaged, quite lovely. I hope people stop using cardboard soon, but for now, it's just an annoying thing.
All right, it's worth the wait, I promise. So this is Mount Sinabung in Indonesia. And yeah, those are fields. So you can tell that it's just slightly more dense. If you look at it, almost everything in it is actually falling downwards, right? And because it's got all this ash, which is dense. At the same time, sometimes you can get new columns forming. So you get this kind of billowing. I always think of it as kind of a broccoli shape. And this is from cold air being entrained into the hot cloud, and then that cold air expands, right? So that's what's, everywhere you look, you'll see things billowing and expanding. At the same time, that whole cloud is still way denser than the surrounding cold air, and it's just going to fall down the slope.
River channel up there.
Yeah, and of course they can travel very fast. This can happen without without really anybody being able to get warning. And that's what happened in. Okay. All right, we'll skip that one then. All right, so what about the power of pyroclastic flows? This one is always a pretty good image to kind of convey things. This is from Mount Lamington in Papua New Guinea in, I think, 1950. And that is a jeep that has been picked up and impaled on broken tree trunks. So this particular one, unfortunately, destroyed a hospital. And the thing you can see sticking out at the top of the picture there is a flagpole. And one of the people that was there to kind of help and try to deal with things afterwards, they took very detailed measurements at this flagpole. And then, because they knew what kind of steel it was made out of, they actually managed to estimate how much force it would take to bend it like that. And then, depending on whether you think it was a very dilute blast that was effectively just air with a little bit of dust in it, a little bit of ash in it, or a denser flow with a lot more ash in it, you get velocity estimates of between 220 miles per hour and about 100 miles per hour. So that's how fast it came through. So we get these different deposits from ash, right? We can have, if you get ash that rains out from a cloud, then it's like snow. It will blanket topography evenly. And if you get a very dense pyroclastic flow that will actually stick to valleys, then you'll get something that the deposit is really restricted to valleys as well. And in between, you can have something we call a surge. So the initial blast from Mount St. Helens was a surge. Some of the things that came through Pompeii, for example, were also surges. They're kind of dilute, but they're still traveling mostly sideways. So they can actually climb over topography, but they'll leave thicker deposits in the valleys. So we can study the deposits and figure out what kind of event produced any particular eruption. There's Mount St. Helens before and after. So the after photo, it may be not immediately obvious from the back of the room. The triangular thing there is all cloud, and it's mostly coming from this resurgent dome that started growing in the crater of Mount St. Helens after the big explosion. So the top is completely gone from between the two photos. Some more recent ones, Merapi. So this is next to a city in Indonesia called Yogyakarta, a very old, famous city. And a lot of people live on the slopes of Merapi. Again, there are many benefits to living close to a volcano, and that typically the soil is very fertile. It's a good place to farm. as long as you don't get caught in an eruption. So this particular eruption was better documented than most because there were actually a lot of international journalists there covering the aftermath of a tsunami, and then this happened. So unfortunately, pyroclastic flows here killed about 350 people. These are villages, you can see how far away we are from the actual volcano, and this is the level of devastation in these villages. We talked about temperatures earlier as well, so this is a photo inside a house that wasn't destroyed, but that's the stereo. So you see ash got in, and clearly it got hot enough to melt plastic. So of course, a very famous example of the effect of pyroclastic flows on a town is Pompeii. So I was lucky enough to be there just a few weeks ago. The first thing that struck me when I set foot in Pompeii was the streets are paved with lava. Right? So it's kind of an obvious thing, really. They used the local stone to pave the streets, but they didn't know that Vesuvius was a volcano, and they didn't know that that kind of rock came from lava. But yeah, anytime you're in a place that has the streets paved with lava, you know there's probably some fairly dangerous volcanoes nearby. Anyway, back to temperature again. This is a really interesting study that looked at the direction of the pyroclastic density currents and the temperature as they moved through Pompeii. And so the picture up there is actually from Herculaneum. It was the best picture I took of charred beams. But you can use charred wood. You can use its reflectance in the infrared to tell you how hot it got. Right? So it's analogous to a way that we use to determine the grade of coal, for example, if we're mapping coal reserves. And so you can get temperature estimates, and then they use the direction in which things got knocked and so on to determine the direction. And so we can map out the direction and temperature history of the flows as they moved through the town of Pompeii. And you can see that when they first arrived, so Vesuvius is up to the north there. When they first arrived, they're coming in at nearly 300 degrees C. And then the city walls actually diverted it quite a lot. It stayed very hot, flowed around the walls and around this side. The stuff that came in was moving slower and had cooled down, but of course it's still, 180, 250 degrees C. No one's going to survive that. So, anyway. I don't know how many of you have read actually I forget if it's called Vesuvius or Pompeii. There was a book a few years ago by Robert Harris, which is a very good dramatization of, it was the Museum of Art and Archaeology book about 2 years ago. Anyway, there's a really good scene near the end where they actually go and investigate the summit of Vesuvius, which of course, we can do again now, but it doesn't look the same as it did prior to AD 79. I did have a chance to go look at the summit of Pacaya in Guatemala. So this is very close to Guatemala City. This was 2010. And it was being fairly active at the time. We were there to actually study the lava flows. We weren't really supposed to go up to the summit because, as you can see, there's a lot of sulfur. And you have to be careful not to be asphyxiated. But went up and had a look, and it was absolutely beautiful. But it did explode about 4 months later. So this is actually a town that we stayed in. It was near to Guatemala City, so that's the airport. And that's what the summit looked like afterwards. So there's now this enormous deep crater in the summit. Actually, the whole volcano was kind of split in two. There's a big crack down it, which is very concerning for the future because it's now a lot less stable. But anyway, so now we've talked about both the red volcanoes and the gray volcanoes. So the lava flows and the explosive eruptions. I want to finish just by discussing briefly how often volcanoes erupt, because I know there's a perception right now that, especially since we heard a lot about Hawaii, and then there was Guatemala as well, and there have been a few others, there's a perception that volcanic activity is really increasing. So this week, so I get the Global Volcanism Program weekly bulletin. So this week, there were about 15 ongoing eruptions and about 3 new eruptions. 3 new volcanoes started erupting, and that's where they are. And all of this year, there have been 29 new eruptions and 69 total, which means there were another 40 that were actually ongoing from the previous year. In 2017, there were 31 new ones and 72 total, and the average for the last decade is 36 new and 79 total. So things are actually going on pretty much as usual. Of course, not all eruptions are equal. I haven't really talked about why volcanoes are where they are, but one thing that's really obvious here is the ring of fire around the Pacific. And so geologically, this is where we have subduction zones. These typically produce very water-rich magmas, and hence you're much more likely to get the gray volcanoes, the explosive kind. And that's what we see most of the way around the Pacific. This one right here in the Indian Ocean, that's Réunion, which is the French version of Hawaii. It's actually officially part of France and part of the European Union. And very much like Hawaii, but French. Anyway, yeah. So as I said, not all eruptions are the same. We have a logarithmic scale, just like with the Richter scale for earthquakes. A magnitude 5 on the Richter scale is only a tenth the size of a magnitude 6, right? And only a thousandth the size of a magnitude 8. So we have a similar logarithmic scale for volcanoes, which we do based on how much stuff got erupted. And then we have different styles of eruption. I won't go through all the details here, except my favorite part of it is the descriptions. So we have like code names that, you know, the Strombolian or Hawaiian. Most of these are named for particular volcanoes, right? The only exception being a Plinian eruption, named for Pliny the Younger, who described the eruption of Vesuvius in AD 79. So it's actually named for Pliny the Younger, although a lot of people think it's named for Pliny the Elder, who died in the eruption. Obviously, if you're going to have a style of volcanic eruption named after you, you are not going to have survived that eruption, I think. But, anyway, he actually died of a heart attack, so wasn't actually killed by lava or anything. Anyway, so there's some examples, but the two things to take away. One is that geologists quickly run out of words to describe how bad things can be. So if we look under description, Hawaii is an effusive eruption, right? Or sometimes gentle if it's a little bit more feisty. Stromboli is the lighthouse of the Aegean. It's the famous volcano that produces things that look like fireworks. So that's explosive. Volcanian, something like Cinnabung in 2010 would be, which we saw a video of, would be catastrophic. And then up to Cinnabung is a category 2. Lassen, 1915, Lassen in California, which is not a very well-known volcanic hazard, but interesting one. So that's catastrophic. And then Eyjafjallajökull, the very hard to say Icelandic volcano from 2010, or Mount Pele in 1902 that destroyed Saint-Pierre, is cataclysmic. And then, St. Helens, 1980, Vesuvius, AD 79, a Plinian eruption, we're on to paroxysmic. Krakatoa, 1883, Pinatubo, 1991, colossal, and then we just basically gave up, and then we've got super colossal and mega colossal. But the key thing here is we've not really seen, actually with the exception of Tambora, but we know a lot less about Tambora in 1815 than we know about Krakatoa in 1883. And that's largely because Krakatoa happened right after telegraph cables had been laid around the world. And there was actually fairly rapid communication, almost real time, between places near Krakatoa and the outside world. Tambora we don't know so much about, except that it was really bad. And then most of the other really big eruptions have not happened. Not many of them have happened in recorded history. So there have been a couple. Taupo in New Zealand. Of course, there's the eruption that produced Santorini in Greece, which is thought to be the cause of the myth of Atlantis. That the whole island basically exploded and was devastated, and is now almost entirely below sea level. Anyway, so we have very, very different sizes, very different magnitudes. As well as the size, the other important question is how often do these things occur? So this is eruptions of Vesuvius from 0 to 1200 AD. We had about 12 and 1200 years, so okay, every 100 years. But then we've had 9 since 1631 and 1944, suggesting more like a 40-year recurrence interval. The other thing is we've not had an eruption at Vesuvius since 1944. We're almost twice as far out as we should be on average. And that's always a bad sign, because we think, deep down where the magma is being generated, that probably happens at a fairly constant long-term average rate. And if you don't have an eruption for a while, it's like, I'm trying to think of a good analogy and failing. But, we're basically building up pressure. We're building up a supply of magma that is ready to erupt. And if we don't bleed it every 40 years and have a small eruption, we're going to end up having a much bigger one. And the problem there is that that's Vesuvius as seen from downtown Naples. It's right there. Actually, Naples has other problems. So there's Vesuvius, there's Naples to the left, and there's Campi Flegrei, which is actually a small version of Yellowstone, just on the other side. So this had a magnitude 7 eruption about 40,000 years ago, produced about 500 kilometer cubed of ash deposits. And if that happens again, that will be a real problem for all of Italy. We've documented 20 eruptions in the last 10,000 years, so about a 500-year average recurrence interval. And the last eruption was 480 years ago. Now, it doesn't do to be too precise. This is not something you can use to forecast, to predict. Well, you can use it to kind of forecast an average. You cannot predict a specific event, right? So, but we know that Campi Flegrei should probably have an eruption soon, as well as Vesuvius. In the U.S., of course, we've got Yellowstone, which is actually a volcano that's been moving across the U.S. because it's over a mantle plume, a hot spot, which is like a candle, and the North American plate is moving over it. Led to, of course, a series of spectacular, very large eruptions. We've produced 3 of these calderas, these huge craters, in the last 2 million years. Crater Lake is a well-known example. Crater Lake is minuscule compared to Yellowstone. But basically what happens here is you empty the magma chamber, and the rock that was overlying the magma chamber falls in. And so these are often super volcanoes, which is not a very scientific word, but it sounds good. But these are things that can have continent-wide consequences. So these are ash deposits from the 2 biggest Yellowstone eruptions and the Long Valley caldera, which erupted 760,000 years ago. And then there's Mount St. Helens for comparison. So the Mount St. Helens ash cloud did circle the Earth, but that's actually deposits that would be recorded in the geologic record. So a Yellowstone type event is a whole different order of magnitude, quite literally. Yeah, there was one, the last one of this magnitude occurred 73,500 years ago at Toba, also in Indonesia. And it's thought that, or it's been suggested that the human population crash at this time might be linked to that eruption, as we would have had basically a volcanic winter. Anyway, this point of this slide is just to say that more destructive events happen less frequently, right? And smaller events happen more frequently. That's true whether it's earthquakes, volcanoes, or anything. The USGS just redid its volcano hazard review for the US and identified these are volcanoes with very high, etc. categories. Just notice there are 18 volcanoes that are classified as being very high threat, some of which you'll be very well aware of, like Hawaii, Mauna Loa and Kilauea, but then also Mount Rainier, Mount St. Helens, several in the Alaska, the Aleutian chain. You may not be so aware of Mount Lassen in California, which is a very good place to visit, by the way. Anyway, all right, I'll take questions.
All right, if you have any questions, please raise your hand and I'll bring you a microphone.
Has the use of drones changed to volcanic research a lot?
Yeah, that's an excellent question. So yes, it has, although not as much yet as it will do. So the question is about drones. I'm part of a team that is putting in a proposal to NSF right now to study the 2018 lava flows in Hawaii. And one of the reasons that we really want to do it, we all study rheology. What we try to do in our research is to link the experiments we do in the lab to the observations we have in the field. Typically, our field observations are limited to going to a lava flow, looking at it, measuring it quite carefully, but we're trying to infer how it was emplaced. In the case of the 2018 Hawaiian lavas, people not only flew drones over it, they parked drones over it for a few minutes. So we have very stable footage of the lava flow moving. So we can get its velocity field. Sometimes some of them had infrared cameras, so we can get temperature measurements as well. So we can really closely correlate our laboratory experiments and our numerical models with what actually happened. So yeah, it's a huge thing. Lassen, I have a PhD student. We're trying to get permission to fly drones at Lassen next year. It may not be obvious, the kind of jaggedy thing on the left skyline is a lava flow. And there's a little bit of it just on the right skyline as well. This kind of lava flow and dome built up in 1915, and then it all collapsed in a catastrophic event. But we were there this summer kind of mapping it and trying to figure out how big it was and exactly how it got out of the vent and how it would have been emplaced. And but it's a long way to get up there, and it's very difficult terrain to walk around. Some of it's really quite dangerous, and there are places we just won't go. But we can send a drone there, and the problem is it's not only a national park; it's also a wilderness area. So the chances are we won't be allowed to, but we're going to do our best. But yeah, there are things you can see with drones. I mean, I'm convinced in geology they're going to completely revolutionize fieldwork in the next decade. We all kind of grew up walking around with our maps and our compasses. So GPS was the first thing that really revolutionized things, and being able to take digital photos and have tablets and actually take a photo and draw on it in the field. But fieldwork with drones is going to be a whole new thing. We actually have a faculty member doing a class on using drones for geology fieldwork next semester. I think it's going to be very popular.
Are you familiar with the Tanzania research team that went down? I think it was in Tanzania. It was a volcano. They went down in there and set up these instruments, repelled down inside. It was on KMOS here a few weeks ago. And I didn't know if you knew any of the current results that they...
I'm not sure do you know what volcano it was?
No, I'm sorry, I can't.
Yeah, so I mean, Oldonyo Lengai is the well-known volcano in Tanzania, which is weird because it's carbonatite. It's basically molten limestone. So it's not silicate. It's much lower temperature. And it's really, really fluid. So I don't know about that particular one. But I have friends that work at Nyiragongo in the Democratic Republic of Congo, which has a permanent lava lake there. They've set up a whole bunch of cameras and so on to look at that, like they have set up at Hawaii. I mean, the main thing with volcanology, right, is that we, for the most part, up until the present, until about now, and in some places it'll be another decade or more, we have the technology to really study volcanoes very, very well. But we need long-term monitoring, because for the most part, we react. A volcano erupts, we go there and look and see what happened. But that means you missed it happening. So what we need is monitoring that is there all the time, and we need, of course, seismic and gas, but we need just video, and we need infrared cameras. And it's expensive, and there's very few volcanoes. I mean, basically, Kilauea is the best monitored volcano in the world, and we have all that there. But most of these other volcanoes, we just simply don't. And in some cases, it's lack of funding. The guys I work with in Guatemala, they have a very hard time getting money from the government to support their research. Other times, Lassen, there was an argument a few weeks ago. I know USGS scientists wanted to put another seismometer on, I think it was Mount Rainier, But again, it's wilderness area, and the Park Service denied them the permit to do it because you're not allowed to take mechanized stuff into into a wilderness area. So it's an interesting balance. Like, I'm a strong proponent of maintaining wilderness areas as well, but you have to find the right balance.
You surprised me with showing a plume under Yellowstone and the plate moving over it. How would you compare or contrast that with Hawaii, the Hawaiian volcano?
Yeah, so normally we think of the plume and plate model. Hawaii is the classic example, but basically anywhere that you have a linear chain of volcanoes, that's probably what caused it. So normally volcanoes occur either in arcs, and that's usually plate boundaries. So the ring of fire, if you look closely, it's actually a whole series of curved segments, because that's what happens when you cut a sphere with a plane going down, and it's actually a plate going down into the earth that does that. And that's why those are all arcs. So we often talk about island arcs, for example. Hawaii, it's a straight line. Yellowstone, it's a straight line. And that is a hot spot in the mantle that the plate is just moving across. And so the current activity tells you the direction that the plate moved from, and the older activity is stuff that already passed over the plume. So for Hawaii, for example, you've got the Hawaii Emperor chain of seamounts. And actually, it's Midway Island that there is a kink, which is about 34 million years old, I think. And that tells us that the plate motions actually changed at that time. In the case of Yellowstone, so we have this series of calderas starting out on the Oregon, Idaho, Nevada border right here about 15 million years ago, and they just get progressively younger along the Snake River Plain to present-day Yellowstone. So that's our model. Now it's different a bit different in that it's a continent versus oceanic plate, but it's effectively the same thing.
If Yellowstone was going to erupt again, when would it erupt?
All right, so actually I would say it's not an if, it is definitely a when. Yellowstone's been active for more than 2 million years, and there have been a lot of eruptions, actually. There have been 3 really big ones. So one at about a bit over 2 million years ago, one at 1.2, one at about 640,000 years ago. Those are the ones that produce the clouds of ash, that would, for example, devastate farming in the Midwest, right, if that were to happen again. But they're pretty far apart. Now, it's been 640,000 years since the last one. I do think there will be another one. As you saw, in the last 15 million years, we've had, of the order of 15 of these things, not always in the same place. It's gradually moving eastwards. So I'm sure that there will be more of them. I don't think there's any reason to think they'll be in the next few decades or centuries. But I can't say that it won't be, nor would I. What's much more likely, though, is a small eruption at Yellowstone. So Yellowstone, in between the really big eruptions, there are small eruptions that produce lava flows, both basalt and rhyolite. Usually not really explosive things. Actually, they'd be really cool to go look at and relatively safe. So there've been basaltic lava flows. There are some great columnar jointed lavas there that look like something you might find at Hawaii or out in California. There are these big, thick rhyolite lava flows that are, be more like the things from Santiaguito, very slow moving. They happen, much more frequently, every few tens of thousands of years. So if there is an eruption at Yellowstone, and I'm sure there will be, the next one is most likely to be a small one that won't be really bad. But we are as a community now, we're definitely focusing on this as a problem. There was an article came out a few months ago on what the year prior to a super eruption would look like, because we think we know some things about super eruptions. First of all, you have to mobilize a huge amount of magma you're going to erupt it, you have to make it mobile, right? Which means it has to be more fluid than it is normally. There's magma under Yellowstone right now, a huge body of magma. It's almost entirely crystalline. It's almost entirely solid. So if there's going to be a big eruption there, there has to be a way of melting it. You need to either intrude fresh hot magma from below that could help with melting it, or potentially a wave of water or something seeping through it might be able to do it. Anyway, but either of those things would be accompanied by changes that we could detect. So anyway, the short answer is I am not going to predict when it will happen, because I'll get it wrong. It'd be embarrassing. And it would be irresponsible. But there will be eruptions, but they're most likely to be small ones until we get a big one.
So in that video that you showed the lava flow that was going down like a few meters a day, and it was only because of the slope of the hill, is it possible to somehow alter the slope of the hill so that the flow would stop on other such flows?
Right, so actually at Santiaguito, that's actually a steep slope. So that lava is so sticky that it wouldn't have moved at all if it were on a flat slope. Because it's on a steep slope, it moves a few meters a day. But if you think about a more fluid lava, like a basalt, like in Hawaii, for example, then absolutely, that's something people have certainly thought about and occasionally have tried. So the most famous examples are probably on Mount Etna. I think it was in the 80s, it might have been the 90s. They actually dropped concrete blocks in front of the lava flow in an attempt to divert it, with limited success. I think the lava was basically just about done at that point anyway. They might have sent it around the side of one building. Jaime in Iceland in the 1960s, I think, they did actually what Tommy Lee Jones does. Anybody seen Volcano? Came out the same year as Dante's Peak, even less scientifically rigorous. The coast is toast. Anyway, it's fun. So in that movie, they actually get a bunch of fire trucks and they just hose down the front of the lava flow to try to stop it. They did that in Iceland in the 1960s, it doesn't really work. So. With regard to this, actually, I had a PhD student who just finished who was studying the effect of slope on how lava flows move, because actually there's a very non-linear effect there. And so the main thing you can predict about where lavas will go is they will go downhill. So whenever we do hazard maps on Hawaii, the one place you don't want to live is in a valley, basically. In terms of changing the slope, in response to an ongoing eruption, that would be a really difficult thing to do, because you'd have to move a lot of earth around very quickly. In terms of a long-term planning, yeah, if you can make sure that people only have houses that are higher up, and there are maybe actually, like irrigation channels, actually have lava diversion channels, absolutely, that could be done. It would just be really expensive. In Japan, they have a similar thing for pyroclastic flows. Around Mount Unzen in Japan, they have these huge earthworks, and they're all done by robots. It's really cool. So because it's a very dangerous place to work, so they have all these self-driving vehicles, but they're all construction vehicles, and they build these huge spillways to guide pyroclastic flows to keep them away from the town. It's absolutely amazing. So it can be done. It's very expensive. And in Japan, there's kind of the collective will, yes, we're going to do this, and the government pays for it, and people pay the government taxes to make it happen. But it's not cheap.
All right, let's have another round of applause for our speaker.
Of course, the real question is, your kids ever play the floor is lava?